All right, now I trust that he will get there. So then actually let's get started and I'll introduce Johannes quickly. So it's a pleasure to have Johannes Zeiher as our second distinguished speaker today. So his background is he studied in Munich and then he thought, well, Munich, and then he moved to Cambridge and then he did his master's there. And then he thought that, oh, Munich wasn't so bad after all. And he came back to Munich, did his PhD in the group of Immanuel Bloch. And there he worked on, optical lattices and excited atoms to Rydberg states, did some Rydberg dressing. And for that, gained him his PhD. He got the Otto Hahn Medal by the Max Planck Society for his achievements during his PhD, which is quite a distinction. And then he went away from Munich again, did a postdoc with Dan Stamper-Kern in Berkeley. And then he thought, let's go back to Munich. And then he started his own group here as a PI. And it's a pleasure to have you here, Johannes. So stage is yours.
Thanks a lot, Fabian, for the introduction. And thanks to everybody for being here, for making it here, actually, despite the weather. And of course, also thanks to MCQST for this nice opportunity to talk here in the colloquium and actually give a little bit of an update on our work on quantum simulation and quantum computing with neutral atom arrays that we're doing here at MPQ. Where, as Fabian was saying, I'm actually working as a group leader. So here you actually already see some fun that you can have with these systems. So basically what you see here is not quite single atoms, but single microtraps that are loaded with multiple atoms. So this is a single shot. And this is obviously a Christmas theme. And this was produced by the Strontium Rydberg lab here at MPQ. And towards the end, I will actually come back a little bit about telling you about that platform. What I actually want to do before that is I basically want to first of all tell you what motivates our work. So what are we after actually in the group? And so the big motivation for us is to basically be able to understand, control, and create many-body systems. And the platform obviously is individual atoms, individually controllable atoms. Why are we interested in that? Well, I think there are actually several reasons. This is a little bit of a personal list that I think is what motivates me at least. And so first of all, I'm very much interested in the fundamental aspects that you can study. So basically, these systems allow you to realize to study strongly correlated systems, to look at transport out of equilibrium dynamics, and also, for example, phase transitions that emerge in these systems. Of course, there's also the aspect of new technological applications that basically in these systems, you can study phenomena that are related to high TC superconductivity. You can study exotic magnetic phenomena and with long-term technology perspectives. And of course, also there's this aspect of being able to potentially realize quantum computers in this platform. These systems can also be used and have actually successfully be used to demonstrate that they can improve measurement and sensing. So two examples are atomic clocks to sense time and atom interferometers to sense, for example, gravity or exotic forces, for example, something like dark matter. And last not least, I think it's a very interesting frontier at the moment to actually think about how you can use these many-body systems, these interacting systems, to realize novel light-matter interfaces, to make to realize this connection between matter, so atoms, and photons that you can actually use to transmit information. And so I think these are many different facets of how you can actually use these interesting many-body systems. And what I will focus on in this talk is actually, as I already said, I want to focus on systems of neutral atoms, and actually specifically systems of neutral atoms that interact via long-range interactions. So let me briefly motivate why long-range interactions. So what's the point about long-range interactions? And this, again, is a very personal point of view. So I think there are actually, let's say, broadly speaking, two very interesting aspects there. So the first one concerns this idea of fundamental research. So can we do quantum simulation with these systems, and what sort of quantum simulations can we do? And so I would say at a very high level, these systems with long-range interactions, actually systems where we have some sort of competing length scale. So first of all, you have a length scale that, for example, could be a lattice constant or a distance between the atoms. And in addition, you have this length scale that is associated with the long range. And so this is usually very interesting in terms of the physics that emerges, because you can have competition between those two length scales. So two examples I want to show. So first of all, an example where you have a lattice. So let's consider this 1D chain of lattice sites. And on each and every lattice site, you can have an atom or not. And these atoms can hop around in the lattice with the rate t. If they're on the same side, there's an interaction strength u. And in addition, you also have an interaction that acts when two atoms are on different lattice sites. And so if you look at the phase diagram that you get from this kind of simple model, right, there's only like 3 terms. then this is already quite rich. So focusing first of all on the case where you don't have a long-range interaction, so where V, this extended this nearest neighbor interaction is 0, we see there are basically two phases. So there's a so-called superfluid phase and a mod insulating phase that you reach when you increase the interaction between the atoms. But then when you turn on this long-range interaction, this V, this just interaction of an atom, on neighboring sides, you see that the phase diagram becomes very rich. So in addition to the superfluid and the mod insulator, you get new phases. You get a so-called density wave phase, and you also get an interesting phase that actually lies between the mod insulator and the density wave phase, which is a so-called Haldane insulator. And that's actually interesting for a very specific reason, which is that actually the order that this phase displays is non-local. So you actually cannot really describe it with a local order parameter, which is the usual thing that you use to characterize phases, at least according to what Landau told us. So this is one example that shows you how rich the world becomes if you just add this one term. There's a similar but slightly different example, which is considering now a gas that is, let's say, just trapped in a conventional, let's say, harmonic trap. So this is a gas of cold atoms, where we know if we cool it enough and you use bosons, that these atoms form a Bose-Einstein condensate, which is also typically superfluid. Now, if you turn on an interaction between the atoms that is not local, so that is not an interaction that is of the nature as this U, where you only see interaction when the atoms are very close to one another, but that is long range, there's actually calculations that predict that the system actually kind of undergoes a transition into this crystalline state where you have isolated puddles, bunches of atoms, basically. And this really is then a crystalline state here. And interestingly, going from the superfluid through these different, these intermediate phases to this crystal, somewhere in the middle, there are actually phases, or is one specific phase that both has superfluid and also crystalline properties. And this is a phase that is called a supersolid because it is superfluid and it kind of shares these features of a solid, which is basically this density order that you clearly see down here. And so this is another example how you can actually make the world very interesting using long-range interactions. So this is kind of the point of view on the quantum simulation part. Of course, you can also take this more technical point of view on the quantum computing part, where if you now think about an array of atoms where the atoms are all pinned, like long-range interactions basically allow you to induce gates, let's say, between an atom somewhere in this array and an atom nearby. And this kind of disk here, this kind of indicates the range of an interaction that you could have in the system. So in other words, if you have this interaction and the radius of this interaction spans multiple atoms, this is actually a way to realize quantum gates, entangling gates. And the state of the art here in the field is actually a recent paper from the Lukin group, where basically what they showed is that you can use such long-range interactions, in this case actually induced by Rydberg interactions, to realize entangling gates that are near perfect. So the 2-qubit gate fidelity in this case was actually raised to more than 99.5%. And this is really on par with other platforms. So it's a really promising outlook on actually using these systems for quantum computing. I should say that neutral atoms are not the only platform that allow you to do physics with long-range interactions. There are actually, of course, many other systems, for example, trapped ions, where people have done a lot of beautiful work, both in the realm of quantum information. I mean, it's well known, most likely to many of you, that the most successful, or some of the most successful quantum computing platform or quantum computing devices are actually trapped ion based. So they are really, really high quality quantum computers based on trapped ions. But there also have been a lot of beautiful results obtained in the realm of quantum simulation of, for example, spin models with trapped ions. There are also magnetic atoms that I'll come to later. These are basically long-range interacting via their magnetic dipole. It's a much weaker interaction than, for example, for trapped ions, but still in dense ensembles, you see very nice effects that are actually similar to this in nature to this density wave modulation that I was describing on the previous slide. And then last not least, there are also dipolar molecules where people have actually in a controlled way associated two atoms to form molecules which then interact via electric dipoles, and they can actually also interact via these electric dipoles over quite long distances. So again, what I will talk about here are neutral atoms, and specifically I will actually tell you how we can realize extended Hubbard models, so Hubbard models with this long interaction using Rydberg dressing. Then I will briefly come also to quantum computing with neutral atoms and give you a bit of a perspective on how we can scale up these systems. All right. So first, I want to introduce the workhorse, basically, of the experiments that I will describe in the following. This is the so-called quantum gas microscope. So what is a quantum gas microscope? Well, as the name implies, it's a very good microscope to detect quantum gases. And what does that mean? Actually, it means that what we can do here is we can prepare single two-dimensional systems of neutral atoms that we can trap in such an isolated plane in a vertical standing wave that you see here indicated as these different slices, and that we can actually subject to additional horizontal optical lattices in the plane that then lead to horizontal, modulated potentials, so horizontal lattice potentials. And in the end, when we, for example, do a quantum simulation, what we can do with this quantum gas microscope, we can actually freeze the density that we have on these lattice sites, and we can read out each and every lattice site and tell whether there's an atom or not on this lattice site. And so we have basically a single atom sensitive device that has local lattice site resolved resolution, and that turning this around can also be used to address individual lattice sites for single atom control. Why is this actually interesting? Well, it's interesting because it allows you to actually get a new glimpse into many-body physics. So if you want to think about it this way, then what you can do with this quantum gas microscope is actually really get snapshots on the many-body wave function. So think about this complicated many-body wave functions that you get after your quantum simulation. Then the quantum gas microscope allows you to kind of, if you repeat the system, the experiment many times, allows you to get snapshots, and you can really analyze these images and look at, for example, correlation signals that describe the physics that happen, and like that really get new insight into many-body physics. Now, in our case, this quantum gas microscope is very specific. So what we have at our disposal to use for quantum simulation are actually two kind of techniques, two technologies. One is basically the Hubbard toolbox that I will describe in a second in more detail, and the other one is the Rydberg excitation. So we can basically couple the atoms that we have in this optical lattice from the ground state, electronic ground state, to highly excited states, so-called Rydberg states, using a single photon UV transition, and by that actually make them long-range interacting. And I will describe in the following how we can actually combine these two things. So first of all, what does this Hubbard toolbox imply? What does this mean? So the Hubbard regime, very generally spoken, is the regime where we can actually describe these single atoms that are, let's say, that we use in these quantum gas microscopes in the so-called Hubbard regime in the single band approximation, which means that we can write down a model that has essentially two terms. One term is a tunneling term. So it describes basically how an atom can hop from one lattice site to another lattice site with a rate j. And the other term is actually an interaction term that describes what happens when you have two atoms on one side, which is actually that they, in our case, repel with a strength equal to u. Something that you can look at in this Hubbard model is this very famous superfluid to Mond insulator transition, which basically describes the transition where you start from a system where u is much smaller than j, and then you, by increasing the lattice depth, reduce j, so you increase, in other words, the ratio between u and j, and so you can go from the superfluid state into the Mond insulator state. And the Mond insulator state is a special state in this case, because the Mond insulator state is a state where you know with very high fidelity that you have exactly one atom per lattice site. Whereas when you have the superfluid, you see there's much more sort of disorder, so it looks much more random. So the Mond insulator state is actually a very well-defined state that is atom number squeezed locally. And this is also a state that we very often use as a very good starting state for experiments that we do, because we really know very well what's going on in the system. So this is the Hubbard regime. Now coming to the Rydberg regime. So what we can do, for example, starting from such a Mond insulator, is we can actually couple the atoms that in this case would all be in the ground state, let's say the 5s1/2 state. We can couple those atoms to the Rydberg state, and we can actually define a spin model that lives in these two states. And now it turns out that if you write down this model, what you obtain is basically an Ising-like model. So you have a transverse field that is describing how fast you couple the atoms from the ground state to the Rydberg state. You have a longitudinal field, which is basically given by the tuning that you apply from the excited state. And this is something that is very unique to these Rydberg states, because they're so highly excited, they actually strongly interact. And so you actually have a strong interaction between these Rydberg excitations. And a consequence of this strong interaction is that if you start, for example, from such a Mott insulator and you drive all the atoms at the same time to the Rydberg state, is that actually the system tries to minimize the energy. So it tries to actually push these excitation as far out as possible. And so you see these very beautiful ordered structures. You see basically an ordering of spin excitation if you drive the system. And this is really just a consequence of the competition between this interaction, which tries to push the atoms to the side, and the drive, which actually tries to put in excitations into the system. And so these are actually pictures that we obtained in this quantum gas microscope about 10 years ago. And I should say that, of course, in the meantime, there have been many, many beautiful experiments in tweezer arrays, which actually showed, very different facets of this physics. For example, that this can also be described as an antiferromagnetic ordering and the realization of an antiferromagnet. People also showed that you can have gigantic entanglement in these systems. So it's really a very active field of study. All right. Now, I said our goal is basically to combine these two sides, to combine the Hubbard side and to combine the Rydberg side. Now, I want to describe to you how we can do that. Before doing that, I want to describe what is the problem in doing that. And so the problem is actually, if you want, the Rydberg decay. So Rydberg atoms are highly excited. That also means they have a rather fast decay timescale. Now, rather fast, I should actually put in context. So if I say rather fast, it's actually rather fast compared to the Hubbard parameters, which in our case are for the interaction on the scale of a kilohertz, maybe 500 hertz, and tunneling is smaller than that, right? So that's required in order to get to the Mott insulator. But on the other hand, if I compare this Rydberg decay to the characteristic timescales of, for example, interaction between two Rydberg states, or also the rate at which I can couple these Rydberg states, then it's actually rather slow, if you want, because these interactions between Rydberg states can be up to gigahertz, and the coupling can be up to megahertz. And of course, this is required in order to look at this spin physics that I was advertising 2 slides ago. So in that sense, it sits here in the middle. But of course, the problem remains, if I want to use this Rydberg interaction here, and I want to kind of bridge this gap to the Hubbard tunneling, then I have to kind of think of something, some idea to get around this. And of course, this would be quite nice because of what I told you in the beginning, the combining basically this Hubbard physics with these long-range interactions holds promise, for example, to see phases like the supersolid, or also this Haldane insulator, and many other interesting things. Okay, but how can I get around this problem? So how can I kind of bring these two sides together? So the idea here is actually that there's no reason why I should actually excite this Rydberg state, right? So what I can do instead is I can actually just I can just off-resonate decouple from the ground state to the Rydberg state. And the way I do that is actually basically just coupling off-resonantly. And what that means is I generate basically from my bare ground state a new dressed ground state. That is, if I detune far from the Rydberg resonance, that is basically like the ground state, but has a bit of Rydberg character, which is characterized by the admixture. And this admixture for large tunings compared to the Rabi frequency can be small. What that means now is that, of course, my state is mostly ground state. Yeah, so it actually is mostly stable, but it does have a little bit of Rydberg state lifetime. So it does pick up a little bit of this problem that I told you about, but also it picks up some of the Rydberg interaction. And now what Rydberg dressing is about is basically just compromising between these two. So giving it enough lifetime, basically, while at the same time increasing or not decreasing the interaction too much, if you want. So let's look at these two things very briefly. So what does the interaction actually look like? So first of all, let's look at what the interaction qualitatively is. So here you see basically the characteristic interaction potential between two Rydberg states, which is a 1/r to the 6 van der Waals potential, which at the distance of few micron can be multiple tens of megahertz. I mean, this is just a specific principal quantum number. This can even go up to hundreds of megahertz. Now, this is the bare interaction. So now what I want is I want to now show you what this looks like if I, instead of using the bare interaction, I use this stressed state. And the stress state, if you look at it, actually has asymptotically a similar characteristic. So it's a 1/r to the 6 asymptote, but then the interaction saturates to a finite value. And in addition, the size of the interaction is actually much reduced. And this is basically just a consequence of the fact that I just admix this Rydberg interaction. And so what I get, this can be shown very easily in this two atom model, is I get a switchable light-induced interaction where this soft core height, so this basically constant value for small distances given by omega to the 4 divided by 8 delta cubed. The range is still an extended range, so this range can still be in the micron range. And this is the important part here, the lifetime is increased by the inverse admixture. So if I have a 1% admixture, I can increase the lifetime easily by orders of magnitude, 10 to the 4, for example. And of course, this is the idea to now get into motional timescales. All right, before going to motional timescales, let me first show you briefly how we can actually make sure that these interactions are present. So I now told you in principle how one can do that, but how can we make sure that in the experiment we actually realize these interactions? And so the idea here is actually to do a Ramsey measurement where we measure basically on the ground state a correlated phase imprint due to interactions between two atoms, in this case in F equals 2. The way we do that is we define a second spin state as a reference state that does not see the stressed interaction, and then we open a Ramsey interferometer where we sandwich the stressed interaction, so the stressing light between pi pulse, an echo, and another pi over 2 pulse. And then in the end, we just measure basically in the C direction, so the spin in the C basis. And the idea now is that if we have an interaction between two atoms in F equals 2, then during this Ramsey, what this means is there's a correlated phase shift, and this correlated phase shift can in the end be translated into a spin-spin interaction. And so this is the idea. So let's look at this in the experiment. So here you see basically just a correlation measurement. So this basically measures, takes the snapshots we get in the end, and it basically translates one snapshot and essentially compares it with itself. And what you should then expect is if you have a correlated phase evolution, that these correlations actually show up in a spatially resolved fashion. And so this is exactly what we see here. If we increase the dressing time, then you see that starting from t equals 0, of course, nothing happens because we haven't applied any light. But then you see for close bispins, this correlation to emerge. And actually, this correlation has an extended character. And this is nothing but a trace of this extended range interaction that we realize with this Hubbard dressing. So again, this is this correlated phase that in the end shows up as a correlated spin evolution that we can measure via this G or C2 correlation. If you look closely, I'm writing here 44 microsecond as the maximal evolution time. Now I was telling you something about extending lifetimes. So that means I haven't actually, told you yet or showed you yet. I haven't made this crucial step on how to get to the Hubbard timescales that I was advertising to be in the milliseconds or maybe longer regime. And so actually to get there, we have to do two more things. So one thing that we have to do is we have to actually work with 1D systems for the time being, which we realized some time ago leads to long lifetimes. And there are some physical reasons that I can go into detail about if you ask me afterwards. The second thing that we do, and this is something new, is that we actually know that if you, instead of continuously keeping the dressing light on, you actually do a pulse stroboscopic dressing, meaning that you kind of compress the time during which the dressing light is on during a short amount of time, while keeping basically the average, and you pulse this while keeping the average of the induced potential constant, that then actually this leads to an improved figure of merit. Why is that? Well, it turns out if you only turn on your dressing time for your dressing potential for a short amount of time, you can go closer to resonance. And then because of the characteristic scaling of dressing, you can see if you compare the height of the soft core and effective lifetime to calculate a quality factor, this quality factor scales with the admixture. And higher admixture means working closer to resonance. And so that actually improves your figure of merit. And again, this is actually crucial to understand that even though I have the same average interaction strength, because I've now pulsed this, which allows me to go during the pulse closer to resonance, actually increase this duty cycle or this figure of merit. So just to convince you that this actually works, I'm just plotting here some data. So here you see the effective lifetime as a function of the inverse duty cycle, which is just the ratio between on and off time. And you can see that this increases very rapidly. And actually you can also see, if you just look at the axis scale here, that now for the largest inverse duty cycles, we actually do realize lifetimes that are in the Hubbard regime. So that's actually great. So now really we can work in this extended Hubbard limit. So now we've basically been able to push the lifetime so long that we can realize, in addition to the Hubbard model that we anyways have, this extended range interaction in a regime where it's not dominated by Rydberg decay. And very briefly, I want to highlight three nice works that realized this extended Hubbard model with outer coat atoms before. So first of all, a work from Innsbruck University from Francesca Pellegrino's group in 2016, where they did this with magnetic atoms, and similarly, very recently in Markus Greiner's group at Harvard, where they also realized this extended Hubbard model with magnetic atoms. And second, I want to highlight this very nice paper from Wasim Parker's group at Princeton, where they followed a similar approach and realized this extended Hubbard model with Rydberg dressing. But in their case, they were only able to kind of access very short handling timescales. So what I will tell you in the following is what we can do now with our extended Hubbard model and these long lifetimes that we were able to achieve. And so the first thing that we could think of is actually that we use our quantum gas microscope to kind of imprint a very specific initial state. And this very specific initial state is a state where we place two atoms on neighboring sites. And we actually, in this case, prepare them on purpose in a regime where the interaction is, on-site interaction is very strong. So that we actually simplify the model and we can neglect this on-site interaction and we can look at the competition between J and V. And what we do then is basically just do a quench experiment where we start with this initial pair of atoms, then we quench the hopping energy, so we let the atoms tunnel and we track the evolution. And what you can see as we vary the ratio between V and J is that actually, if you just focus on the probability of finding two atoms on two neighboring sites, that's what's basically a density plot here, that as you increase the interaction, this is more and more likely. So it seems like the atoms or the interaction actually keeps the atoms tightly bound together. And we can actually look at this more closely. If we, instead of looking at the density, we now look at the joint probability distribution, which says, okay, how likely it is to find an atom on lattice site J, given that I found the other atom on lattice site I. So what you see here is, if you look at the diagonal, or actually on all sides near the diagonal, is actually a signal when two atoms want to be close by. So this is basically this signal here. And you see a clear enhanced probability for two atoms to be close. On the other hand, you also see a signal where if I find one atom on side I, then I find the other atom on side minus I, if you want. So this is kind of an anti-bunching, so the atoms spread out. And so it's actually expected that both of these contributions are there. There's the so-called bound state here emerging on the near the diagonal, and there's this free state that kind of has this anti-bunching feature. And so we really take actually this signal here marked by red as the first indication that there is this bound state. And we can actually also characterize this bound state by comparing how fast the bound state spreads compared to the free space, to the free state. And this actually provides us with a good way to calibrate our software. And you can actually see that we can very nicely make these predictions based on an exact model and calibrate our software using these two expansion velocities. All right, this is a high, if you want, let's say a high energy physics in the sense that we made a quench here. Now, another thing that would be interesting is actually to explore physics near the ground state. In order to do that, what we wanted to do is actually wanted to adiabatically basically turn on this long range interaction, this extended range interaction. And we did that now not with just two particles, but actually with 8 particles in a 16-site system. So we prepare a system in a very cold state where you have 8 particles distributed over 16 sites. And what we do then is we just slowly ramp up this extended range interaction, and then we see in what final state we end up. And of course, what you expect is that you see an influence of this long range interaction. And so this is basically also what we see now, basically showing you 4 panels where we vary the final interaction strength. You see as a function of this final interaction strength, how focusing now on the blue curve, starting from essentially no effect, we see how you start getting a strongly negative correlation on neighboring sites, which is actually indicative that atoms try to avoid each other. And this becomes more and more strong as you increase the final ramp depth. What you also see is that on the next nearest neighbor site, you see a positive correlation, which you also can understand thinking about the density here, we have half filling. So if every atom basically starts to push the neighbor away, then in the end, what you would expect is almost like a checkerboard-like ordering. So what you see here is, if you want an onset of this checkerboard-like ordering. And you can also compare this actually to the gray data, where we don't actually turn on this extended range interaction, where basically nothing super exciting is happening. So this is something that we are actually quite excited about. This is really the first time that people could actually see these low energy phases in the extended Hubbard model using the back dressing. I should acknowledge the team here. So mostly Pascal, who was pushing this stroboscopic dressing and the extended Hubbard model forward, and also Kate was helping a lot. And of course, also discussions with Tizian and Annabelle, who helped a lot in initially understanding what's going on. All right, now I'm basically out of time, so I won't have so much time to talk about quantum computing with neutral atoms. But let me briefly tell you what makes us excited about neutral atoms and quantum computing. It's basically the fact that if you think about DiVincenzo and what he told us that a quantum computer should be able to, deliver, then neutral atoms actually all fulfill all of these criteria, these DiVincenzo's criteria. So they're a very promising platform. Up to now, they actually had one flaw, which was basically that 2-qubit gates were not working so well. And here, basically, I want to come back to what I said in the beginning. There's been an exciting amount of progress recently in pushing these 2-qubit gates and the fidelity, especially, essentially on par with what you can have in other platforms, especially this recent result from Harvard, which is now basically the highest gate fidelity that we've seen, really. And you can also see that there's been a lot of progress over just 10 years. And this actually also prompted us at MPQ and within the framework of the Munich Quantum Valley to follow this, success story and use our knowledge and the control of atoms trapped in optical lattices and Rydberg atoms to actually be part of this Munich Quantum Valley and push for a quantum computing platform based on neutral atoms trapped in optical tweezers and optical lattice. And I won't have too much time to talk about all of this, obviously, because Fabian is already standing up. But we are really basically contributing the basic technology hardware layer to this full stack that is the goal, which will be realized as one big goal of the Munich Quantum Valley. So we are really at the basis developing this hardware platform. And very briefly, what our platform is basically similar to what I was showing you, an array of single atoms that we can control with individual laser beams. The big difference now is that we want to be able to control each and every one of those atoms locally with a laser beam to do 2-qubit gates, and also to realize these Rydberg interactions, for example, to realize 2-qubit gates, which is indicated here. Our workhorse will be strontium-88, which we think has very beneficial properties for quantum computing because it has this clock transition, which is highly coherent, which can act as a qubit, and we can realize 2-qubit gates coupling to the Rydberg states as I was describing, or similar to what I was describing before. So this is basically the platform. Maybe very briefly, why am I so excited about neutral atoms in general? So why does this platform, in my point of view, have a great prospect also for quantum computing, but not only, also for quantum simulation? It's basically the scalability. So what you see here is a picture that we obtained in the Strontium Rydberg lab at MPQ, where you can see almost 10,000 atoms loaded in an optical lattice, and you can really, for each and every lattice site, say whether there's an atom or not. And these pictures may look a little bit, let's say, disordered, and they are, because we haven't actually controlled the position yet, but we're actively working on that. So here you see basically one example where we started moving atoms around and actually resorting them into arbitrary shapes, in this case, starting with a square shape, but we are also thinking about how to actually resort them on more complicated structures. And this is really something where, just scaling these systems up, I think has great promise. And with that, I want to briefly thank the whole team. So this is basically the Munich Quantum Valley team working on this neutral atom quantum computing demonstrator, and also the Strontium Rydberg team that did these, took these beautiful pictures of these, thousands of atoms in the optical lattice. And with that, I'm at the summary, and I will leave the summary up, and thank you for your attention.
Great. I'm sure there are many questions. Okay, I'll start with one. What about distances? Like if you have these Rydberg interactions, I mean, as theorists, we want to have them maybe even with the dressing if they're very close. But then there's this spaghetti story that if they get too close, can you say a few words about that?
Yes, I think this in the end. So what Fabian referring to is basically that I presented a very simplistic view of Rydberg interactions, which is that you have a 1/r⁶ potential at all times. Now, the truth is actually that as you decrease the distance between two atoms, of course, you have many, many Rydberg states. And so other 1/r⁶ potentials can actually cross. And so this is in the community running under the name of Rydberg spaghetti, because at very short distances, you have so many potential crossings that it's essentially just a forest of lines. So we've had to deal with that a lot in the optical lattices because we are working naturally at these short distances. So the simple approach is to just basically go down in the principal quantum number, which actually scales the spaghetti, to smaller distances. And then you just basically set the smallest, go to the smallest end that you have to go to in order for the spaghetti not to make a big difference. This is actually very straightforward. Another approach, obviously, is to make use of the spaghetti that you can still understand. And the good news is that we can actually calculate these potentials very well. So this is all let's say in the end, it's electrostatics, if you want. So it's two charge distributions of which you calculate the electrostatic interaction. And this we actually did a lot in the past years to be able to understand and benchmark the quality of those calculations, and they're really excellent. And so then, of course, you can make use of those, that knowledge. And I think this is also very exciting. So I think that's
more questions. Okay, great. I'll start in the back and then we'll work our way up forward.
Hi, Johannes. Thanks for a nice talk. I had one question. You mentioned that when you had this nearest neighbor interaction, you could see a signal of a bound state. So they tended to be close to each other. But then in the many-body setting, you saw a dip in the G2 at the nearest neighbor. So how does that?
Yes, a very good question. So I think it's in the end, it's a different effect, I would say. So maybe first question, why is there a bound state? This is something that it's a so-called repulsively bound state, we think. So the idea is essentially that you're in a lattice, you have sort of a bound spectrum, right? And if you lift like these atoms, if you disconnect them, let's say, to the continuous from the continuous spectrum you have in the lattice, then they would just stick together, right? They would not couple. Like the easiest would be you give them such a large interaction strength that they are entirely lifted out of the continuous band of states you have in the lattice. And so this is this repulsively bound state, and this is sort of what we expect to see here. And of course, what's interesting is and this is also the case here, is what happens if you have residual coupling to these continuous states. Then, of course, this bound state will somehow, will actually not decay, but there's a finite overlap with these free states. And so I think this is quite interesting. One can actually also show that the system maps to an XXC model, and then the bound state that we are seeing here is the same as a Magnon bound state. So it's really a bound state between two spins that are pointing up in a background of spins that point down. That's formally exactly equivalent. Now, the second question on the low energy physics. So there, I would say it's quite intuitive. We have a repulsive interaction, and we have an atoms that can basically freely move around. Okay, with the boundary condition that they are hardcore bosons, so they cannot occupy the same lattice site. But of course, if you make them repel each other, they would try to avoid each other. So that just means that if your temperature is low enough, you should actually see that negative correlation in the G2 that we are observing.
Okay. Here there was another question.
Yeah, my question was just, you mentioned in these extended Hubbard models that you have an enhanced lifetime in the 1D system. And so I was just wondering why that was.
Okay, yeah, so this is something that I would say is still work in progress. So the story is that we tried these experiments very early in 2D systems, very dense 2D systems. And then you actually start getting trouble because of these spaghettis. So there, actually, the main problem is that if you excite a Rydberg atom, and this happens for every Rydberg system in principle, then the Rydberg atom actually has one decay channel back to the ground state and other decay channels to neighboring Rydberg states. And now the problem arises when you decay to neighboring Rydberg states that interact with the Rydberg state that you want to talk to, because that, of course, leads to level shifts, right? That's the interaction. And then, especially for dressing, if you want to be off resonant, but a level shift shifts you in resonance, then this whole argument of saying I trade in, let's say, lifetime for interaction breaks down, because all of a sudden I have a resonant coupling And so my lifetime will be very short. And so moreover, there's actually an avalanche effect because you can basically then excite more Rydberg states, which again can decay into neighboring Rydberg states. And so this basically is a runaway process. And this is something that we saw. And very pragmatically, if you go to 1D, the likelihood to trigger this avalanche is much reduced. And also the likelihood to actually get these problematic decays in the first place are reduced. So I think we are still working on this. So we have some ideas. For example, with this pulse scheme, you can now think about actually cleaning out Rydberg states that are there that you don't want. But we haven't actually tried that.
Here, then we had one more question in the front.
Thank you. I have a question regarding magnetic states and general question about magnetic excitations. So with your techniques, is it possible to kind of look at the dynamics and look at the dynamics of a spin system also under stimulus or excitational drives?
Yes,
there's different magnetic resonance.
Yes,
magnons involved, which would propagate.
Yes.
And so the question is, can you look at the dynamics, or can you stimulate also dynamics?
Yes.
Relate to properties which are potentially known from solid state?
Yes. Oh, yes, absolutely. So this is something that we try to do. So what is a bit difficult for us is to kind of realize, let's say, a transport measurement where you keep a stationary, let's say, voltage difference or some voltage difference, because ultimately our systems are closed, right? So you cannot like bring in particles on one side easily, at least, and pull them out on the other side. But what we can do, of course, is we can look at similar effects in closed systems. And of course, the physics that you're probing in these transport experiments, where you put a voltage here and or magnetic field gradient or something, they're very similar. If you, for example, if you apply a magnetization gradient, or you make a magnetization imbalance, then we can actually look at these magnon dynamics, and we can infer what's going on at a microscopic level. And we actually, I didn't show that at a recent paper where we exactly looked at that for the Heisenberg model in 1D, which is quite interesting because it's integrable. And so we can do that, yeah. So it's sort of these transport measurements, these out of equilibrium measurements are something that we very much like to do.
Okay, maybe one last question, and then we can move on to cookies and coffee and whatnot.
I have a question in terms of quantum computing. So let's imagine like you have such 2D lattice, and you're given a bunch of pairs that you want to make interactions. Then how the time scale increases in terms of the size of the lattice?
Which time scale?
Like if you want to operate some 2-qubit interaction where those 2 qubits can be long range.
Yes.
And then like how would you compare the time that you need for these operations compared to allowing only nearest neighboring?
Okay. I mean,
and what's the advantage for that in this?
This now, I guess if I understand it correctly, asks the question of connectivity. So it's correct. I mean, I drew these disks in the beginning, right? And this basically only covers nearest neighbors. And now you're asking, okay, how can I make one atom here and one atom on the other side of the lattice interact?
Yeah,
that's something I think there are basically, 3 points. So one, if you just have Rydberg interaction, that is kind of short range. The only way to do it, I think, is to basically do swaps. So you basically interact 2 that are within the disk, and then the next 2, and so on. And the good thing is these Rydberg gates are in principle very fast, so 100 nanoseconds. So you can actually cover quite a distance in not such a long time. The second approach is something that they do at Harvard, for example, is you basically pick one atom and you move it to whatever atom that you want to entangle it with, and you place it and you make your local entanglement gate, and then you bring it back, or you just leave it there and you think about where to move it next. The third approach, this is something that I didn't have time to cover, but I can do it now, thanks. It's basically, there is another approach, which is basically to use photons to make this entanglement. And so we actually work on an experiment here. This is a cavity experiment where we want to place such an array of atoms inside an optical cavity. And then what you can think of is that if you have an atom here and you want to entangle it with an atom, let's say down here, rather than moving it or doing swaps, you actually couple it to a photon. And then, of course, the photon delocalizes. You have to kind of put it into a cavity that the atom light coupling is strong enough. And then you can make this atom down here basically interact with this photon again. And like that, you can actually realize a gate. This is not the full story, but it's one way you can do that. So I think this would be my answer.
Maybe I can ask further questions later.
Yeah, sure.
Okay, I hate to say it, but we're pretty much out of time. So let's thank both speakers again. Thanks everyone for coming, and enjoy, the cookies and exchange yourselves.